In the last lesson, we talked about what density altitude is and how it affects the performance of your Skyhawk. Now let's consider some additional ways you can get the data you need to determine density altitude. And at long last, you'll get a look at a practical application of density altitude to determine one important aspect of performance. When you were sitting in your Skyhawk at the airport, it was easy to get pressure altitude. You simply put 29.92 in the altimeter window, right? But let's say you're poolside at a hotel in El Paso, waiting for your passengers to finish trying to buy everything in Ciudad Juarez. It'd be nice to know how your Skyhawk will perform before you go to the airport, just in case you need to negotiate weight compromises with your companions, like telling Cousin Martha that no, she can't bring that 6-foot, 600-pound plaster of Paris surfing monkey. The problem is that the hotel manager won't let you bring your Skyhawk to the pool. So how are you supposed to determine density altitude? Well, just dial up the ATIS at El Paso International using the phone number you found in your airport facilities directory. You'll hear an altimeter setting of, say 29.55, as well as a temperature in degrees Celsius. Now here's a table you won't find in your Skyhawk's manuals, but you will run across it in your aviation career. It will save you some calculation time and provide you a more accurate result than the 1 inch per thousand rule you worked with before. So let's get started on the altimeter settings side and find 29.55 halfway between 29.5 and 29.6. Then move to the pressure altitude conversion side and find the difference between 392 and 298. If your math is the same as mine, your total will be 94. Since 29.55 is halfway between 29.5 and 29.6, divide that 94 in half and you'll come up with 47. Now add 47 to 298 and your altitude correction will be 345. And since it's a positive number, you'll add 345 to the El Paso field elevation of 3,956 and get 4,301 feet. Remember that you can find field elevation on your chart or in your airport facilities directory. So, 4,301 feet is what your altimeter would read if you were at the airport with 29.92 set in the window of your Skyhawk's altimeter. That's your pressure altitude. Combine that with the temperature you got from the ATIS, and you'll use the same chart we used earlier to find density or performance altitude without going anywhere near the airport. But you don't want to spend your days computing density altitude. You want to put those little air molecules to work, right? Well, here's one way to predict a particular performance, in this case, takeoff distance. This chart is designed to help you calculate your takeoff distance based on temperature, pressure, weight, and wind. And it really isn't as threatening as it looks, although you may look at it and say, what is this unlabeled mess? Well, starting here on the left side, you see temperature across the bottom, slanted lines of pressure altitude, a standard ISA temperature line here. Why, of course, it's your old pal, the density altitude chart. It may be a tad squished because there's more space for temperature, but it's a density altitude chart nonetheless. But notice that unlike the density altitude chart we looked at before, there aren't any density altitudes shown along the vertical edge. Should you worry about that? No. Density altitude's value to you is as a starting point for determining specific performance factors. By itself, the number doesn't mean much. After all, we are really looking for the takeoff distance. In this example, the chart maker made all the grid lines the same scale. This really means that when you get to the pressure altitude and temperature intersection on the density altitude chart, you move horizontally to the right, and you've entered this graph at the correct density altitude. We just don't know what that density altitude happens to be, nor do we much care. Now you know that pressure altitude and density altitude are equal at standard temperature. So, the horizontal line passing through this intersection must be 4,000 feet. density altitude. And the line passing through this intersection is 6,000 feet, and so on. So let's say you want to calculate the takeoff distance and you have the following information. You have a 2,400-pound airplane. The temperature is 10 degrees Celsius. Pressure altitude is 4,301 feet, and you have a headwind on the runway at 20 knots. Now, on a chart this small, it's hard to be precise, but here's the approximate 4,301-foot pressure altitude line. You climb the 10-degree Celsius line right here, and then move horizontally to the reference line over here in the next chart. Doesn't always happen, but in our example, we've managed to catch a slanting line dead on. Now, you're going to move to the line for 2,400 pounds, which you'll see along the bottom. Find the 2,400 pounds, then follow the line to 2,400 pounds. What you've done is you've taken care of the change in performance because the airplane wasn't at its maximum weight. And aren't you glad you talked Cousin Martha out of that plaster of Paris surfing monkey? So now you move horizontally to your right for the headwind correction into this last grid. You can see that your line arrives at the reference line at a point more than halfway between these two slanting lines. So now you need to locate the point on the vertical line, in this case, the 20-knot line, because that's what the headwind was, and about the same proportionate distance between the slanting lines, right there. What you've done is you've corrected for wind. So now you just move horizontally off to the edge of the chart to the right edge, and you read the takeoff distance, which is about 600 feet. There's 1,000, there's 500, there's 600. Piece of cake. Well, by now you know that temperature and pressure affect your airplane's performance. There's another variable in performance that you don't have any way of measuring from the cockpit. That is humidity. For a simple airplane like the Skyhawk, there are no published data available to help us evaluate humidity's effect on performance. You should be aware, though, that your Skyhawk's performance will suffer somewhat under high humidity. It's only fitting everyone's performance suffers under high humidity. The reason is that water vapor molecules are less dense than air molecules, and the water vapor cuts down on the number of air molecules available to deliver performance. One of those old pilot sayings was even created for this one. It goes, beware the 3 H's, hot, high, and humid. Hot is for hot temperature, high for high altitude, and humid, well, that one's pretty obvious. Beware, because all three are things you can't control. But if you're aware of them and use these tools to help you understand how your Skyhawk performs, you should be able to conduct your flight safely with no performance surprises. And may your only surprise be the one Cousin Martha bought for you in Mexico. A crushed velvet day-glow painting of pool-shooting poodles.